Good morning, good afternoon, and good evening, everyone, from wherever you're joining us from. Welcome to the next installment of tinyML Talks. Today, we have Ashutosh Pandey from Infineon Technologies to talk about exploring techniques to build efficient and robust tinyML deployments. My name is Ravi Sivalingam from Qualcomm AI Research, and I'll be your moderator today. We'd like to thank our tinyML Talks strategic partners, Aeon Devices, ARM, DeepLight, Edge Impulse, Emza Visual Sense, Greenwaves Technologies, Gravity Inc., HOTG, ImageBob, ClickerTech, Latent AI, Maxim Integrated, Micro.ai, NXP, Prophecy, Qualcomm, Kixo, Reality AI, Renesas, Rexon, SAP, Seed Studio, Sensimal, ST Microelectronics, Stream Analyze, SynSense, and Sentient. Additional sponsorships are available. Please contact Olga at tinyml.org for more info. Just a reminder that our big event, the tinyML Summit 2022, is coming up soon at the end of March here in San Francisco. Registrations will be open later this month. And a tinyML Research Symposium will be conducted, co-located with this tinyML Summit, and that's on March 28th. Sponsorships are available. Please contact sponsorships at tinyml.org. A new next event for our tinyML Trailblazer series, Success Stories with Kurt Busch, CEO of Sentient, and moderated by Chris Rowan, is coming up tomorrow morning at 9 a.m. PST. Register now using the QR code on the slide. Yep, and a reminder, our tinyML meetup communities have been growing very rapidly. We have over 7,700 members in 42 groups across 33 countries. Please use the QR code or the link on the top of the page to join our meetup groups, and especially join the one that's closest geographically to you. We also have our tinyML community on LinkedIn with over 2,500 members and 4,300 followers. Please use the link or QR code to join the tinyML LinkedIn community as well. Our tinyML YouTube channel hosts all our talks and various events, including this video, which will be available on our tinyML YouTube channel in the next couple of days. So reminder, our next tinyML talk, global talk, is on Tuesday, February 1 by Mohammed Shafiq from New York University of Abu Dhabi, UAE. And he's going to be talking about energy efficiency and security for tinyML and Edge AI, a cross-layer approach. In addition, we also have several talks later this week after our Trailblazer series on the 20th and the 21st as well. All right, so our speaker today is Ashutosh Pandey. He's currently a lead principal systems engineer at Infineon Technologies, where he's responsible for machine learning solutions, architecture, and tooling. He holds a PhD from the University of Utah and has over 40 papers and patents on speech, audio, machine learning systems, and algorithms. Take it away, Ashutosh.
All right, so, okay, hopefully you guys can hear me okay. So today, anyway, first of all, good morning and good afternoon, good evening to everyone. And I'll be talking about the efficient deployment for robust tinyML systems. And here is agenda of the talk, right? I have actually organized a talk where we will introduce the problem and we'll talk about the system, which is the focus today, that is tinyML. We'll go through the motivation and see where we want to get to, right, through architecture and solutions. And the rest of the talk will go through one by one onto different aspects of the tinyML, right? And we'll go a little bit into what is, how this is deployed today, how the solutions are used today, and where we want to get to. And we'll be taking a short stop after each section. So if there are any questions, right, we'll keep it interactive. And towards the end, we will conclude the talk and hopefully, as a community, this talk will help us get to the, next level. And so that's the goal. So before we go a bit more into technical details, right, here is the team. And I'd like to take a few moments to acknowledge them. and they have been responsible for creating a lot of technical material behind the scene. So, okay, with that, let's get to the fun part, right? So, what is tinyML? I mean, we have actually heard quite a bit about tinyML, and this forum has been, critical to sort of defining, and over the years, kind of taking us to this milestone that we hear terms like low power, privacy, and low latency, right? I added low memory and efficient implementation as well, because when we think about tinyML, these are the aspects that we cannot live without. So with these sort of 5 pillars in mind, we will actually, for the rest of the talk, try to see how we can maintain this in our machine learning solutions while we actually try to, get to the next milestone or next stop. So to get better understanding, what we are gonna do is we're gonna actually compare and contrast against its counterpart, which is CloudAI, and they are often sort of compared in to understand where we want to go or how they are different, right? And this comparison is important to understand what tinyML has done really well versus where it aspires to go, right? So I mean, if we just want to list down the items, you have done that here in a tinyML. If you see a tinyML system where it's running with limited parallel processing with limited precision, and it has limited memory, whereas on the CloudAI it has a bit of freedom in these domain. And what it actually enables CloudAI to do is that it can create solutions which have, for the lack of better understanding, it comes out that it has better performance, right? And I mean, like I said, right, like past few years of work, tinyML community has shown that it is possible to kind of take over many of those tasks onto tinyML domain, right, without sacrificing any of its attributes. But there is still sort of a bit way to go for us. And to keep that perspective in picture, right, what CloudAI is able to achieve while not losing sight of what tinyML is supposed to be, I think we can define where we need to be and how we need to get there is what we will try to talk about today, right? So to take away from this slide is that tinyML has some limitations, and CloudAI has better performance in some areas, and tinyML, we would like to grow techniques in the tinyML domain so we can get to some of the performance aspirations that would eventually add to great user experience, reliable deployments, and it will scale to multiple applications, right? Which is sort of grand goal for machine learning, to scale to as many applications as possible. Okay, so now that we understand what tinyML is trying to do, let's see how do we get there, right? To understand that, we're gonna go a bit more into technical details. So here is a successful tinyML solution architecture, right, which has been curated over the last few years to get to the point where we are. And it starts off with a very well curated data, right? So in a machine learning system where data is king, for tinyML applications, it's even more important. With that well curated data, we go through the model training phase. The other important piece for tinyML is actually quantization, that creates these models which are friendly for embedded devices or edge devices, and that can be deployed in the field, right, in a closed loop manner, and it works reliably. And there are many successful examples, right, that's working today in tinyML community that incorporates ingredients from here. And like behind the scenes, what happens is that well curated data actually leads to very efficient and small neural network models, and we have some examples here that would highlight those points. Also, creating this offline training and tuning flow actually results into very efficient software and hardware implementation, because you are doing architecturally things that are actually eventually going to result into very efficient implementation. So again, we'll see a bit more detail in a bit. Now, I mean, while all that's sort of, well and good, these are also the challenges of the tinyML solutions that sort of, prevents in some cases from scaling, right? We hear terms like, okay, this is a cloud friendly problem, right? Or our edge devices cannot, is not able to handle it. And we have shown that, tinyML is a lot more capable than it was believed to be. And I mean, I believe that, it will continue to be that way. So to solve that, we need to understand, what's sort of preventing it and where do we need to go from here. And that is basically is going to form this talk as well. So here, the well-curated data is very important and have actually led us this far, but often to get to the well-curated data with training and quantization, you can see that how many splits you need to do with data, right? And each of these actually domains have to be, well balanced. And once you have actually figured out an application, you can actually run your system for, a few days to maybe a couple of weeks, and you come out with a very robust solution. It's great. But this also prevents you from scaling very fast to multiple applications, where something like CloudAI can actually, given its, large access to memory and compute resources, it can go and quickly iterate on things from the ensemble learning perspective, from sort of, actually reutilizing data and things like that. So it's important that we pay attention to this and we try to solve this. The other part is the quantization, right? I mean, just the way we have designed the quantization schemes, it is designed to be very efficient, right? Which is great. But however, when it goes to the field, and if there are, I mean, so to speak, out of distribution examples, it may break quite a bit in the sense that, performance can become unreliable and things like that, right? And there are many applications where you don't have lots of data, right? And for the lack of data or for the lack of methodology, if you're not able to scale to those applications, it sort of, is a fundamental flaw in the philosophy itself, right? And finally, I mean, having no monitoring capability is always can create, unsafe behavior in any system, and that is a fundamental flaw, right? So we need to actually think about these issues and try to solve them. And in today's talk, we're gonna actually address specifically, and we'll propose, a few methods how to address them. And obviously, there is a lot more to be done to be for this to solve this all the way. But I mean, at least we'll try to get it started today, right? So with that in mind, let's start with data a bit, right? I mean, we understand the role of data. And in machine learning community, we have heard, there are many ways to handle data, right? You have augmentation, you have, good labeling practices or creating, great data sets, so to speak, right? You have transfer learning, meta learning, deep representations, and probably a lot more. And generally, I mean, if you see that the top three here, transfer learning, meta learning, deep representation, they tend to sort of create your generalized solution. And, you have other practices that actually helps you create very efficient solutions, right? And if we just focus on data and machine learning part of it, right? I mean, at a very high level, it can be said that if you have lots of data that can actually mimic good statistics, you're gonna end up with a, efficient solution. And if you have partial statistics, it's better to utilize prior knowledge, right? From transfer learning, meta learning, and other techniques. And so what we're gonna do here is we're gonna actually look at example where to see how far this is sort of, extends. And we will start with a tinyML approach, which is often practiced. But this example I sort of designed to make sure that we understand where we are, at least today, right? So here is a transfer learning approach, which if the definition is that you have sort of a trained data set that has learned a task, and you try to extend it to another task, right? So there are two approaches that you can employ, where you can train the part of the neural network for the new task, right, which is called discriminator, and the first part, which is often referred to as feature extraction. On the other hand, you can actually train the whole network. And to have a sort of a fair comparison, what we did is that we used the training data set that came with the ImageNet, and then we extended to a face detection task. Here that is kind of shown. And then we started to remove one block at a time, right? And in machine learning or deep learning applications, sort of things are stacked with blocks. And then the implication of removing those blocks is that the model becomes more, smaller and compute efficient and things like that. And here is the sort of overall impact on accuracy. So this is when the fine tuning was disabled, so to speak, and here when it was enabled. The takeaway from this slide is, right, even when you just started with few examples of training and testing, you got pretty decent accuracy, if you compare here and here, right? But this started to drop off pretty quickly, whereas it stays the same. And this kind of goes back to the narrative that, if you have lots of data, right, you might as well actually do the end-to-end training and optimization, and you're going to come up with something that's, compute efficient. Otherwise, you use some generalized approach, right? And transfer learning being one of them. And we'll talk sort of the approach that we have found to be useful. So hopefully this sets the background for deep representation, where what we wanted to talk about is that here is a method that can help alleviate some of the sort of pain of creating this holistic data set while actually keeping the benefits of tinyML compute efficiency. So here is the general blueprint, right? Like I talked about, we have data, we train the neural network over and over, create something very efficient, and go into the deployment mode. Versus the architecture we would like to propose is where if you have data, you kind of augment data with a similar problem. You feed it to these deep models that actually later gets utilized by neural network. And there are many flavors of how to combine them. We will talk about two of them today. And that what we will show here is that if you have lots of data, having this approach actually can even give you a bit more performance. If you don't have lots of data, it does actually help you generalize pretty well. In addition, when we were looking into these deep representations, we wanted to make sure that we kind of create something that can scale to multiple tinyML applications, right? From image to sensors and tracking and things like that. So we kind of looked at these three attributes, which is generalizing to multiple problems, and then it can extend to many applications like denoising, statistical, and classification. And obviously, we wanted to make sure that it's tinyML friendly, right? So it can be implemented efficiently. So the answer came out to be the autoencoders, where we found there are there are different flavors of autoencoders that can actually help you scale in different problems, whereas being efficient and things like that. And the three of the autoencoder flavors we'll talk today is denoising autoencoder, which uses pretty much reconstruction loss. So the beauty of this is that you can use any data set and fit it to any problem you want, because all you have to do is use the data, kind of create a sub-representation and use both as sort of your X and Y, right? So your input and output, and you can get started. Then there is variational autoencoder that uses reconstruction loss and divergence for actually variational inference to compare the distribution with your current data. And eventually it comes, what it comes out to be is a good representation of these statistical parameters, right, that can be used for some applications, and we'll show one today. And the next one is these discriminative autoencoder. And in machine learning, a lot of problems we do is, discriminative classification. And we found that a discriminative autoencoder can be a very powerful tool there. So we applied it to two applications. One is keyword spotting, the other one is human activity recognition. And we will show some results here. So the first one is the application to a keyword spotting. And I mean, for those who are familiar with this, is the problem is that you take these signatures and you try to classify them into one of the classes, right? And eventually you have some pre-processing and you are actually classifying into one of the sounds. Whereas, like I said, that what we did is we used actually different types of autoencoders, and we trained them in a pretty much in a denoising manner, right? Where we took the signals, added some distortions, and tried to optimize it. And we took these intermediate latent representations and used that as features, right? Very simple setup, easy to create, and easy to utilize. And at a very high level, we have run a lot of experiments, which is we have submitted for one of the conferences. But the takeaway from this was that actually most of the autoencoders came out that in a very well-designed solutions where the data was actually very well augmented, right? We used, hundreds of hours of data, and we reached to a point where, we couldn't go beyond. This was able to give us, more performance. And these autoencoders can be designed using, tinyML principle of, making as small as possible and things like that. And they were able to give us extra information that resulted into better performance. It generalized well. And here is a small snippet. And like I said, right, there is sort of a detailed study in a paper. But overall, this was turned out to be a very good compromise for creating something that's tinyML friendly, but generalizes as well. So this is another application which is more for tracking, where we used a variational autoencoder, right? And we trained it in a discriminative manner because this was designed for a classification task. And you can see that, with the very small data set, training data set, we were able to actually improve some of the sort of problematic areas, which you can see over here and here, right? The difference between the first and the second example is in the first example, we had lots of data, right? We had very good data set and we were able to get more performance. In the second one, we barely have any data, but we were still able to get better performance. So all in all, it's a good tool, that we can actually add to tinyML toolbox, and that can, help us improve performance and keep the benefits of compute efficiency. So before I move on to next topic, any questions here?
Yes, actually, we have a few questions. One is about, can you please provide more background on the quantization calibration data? How is it different from the training and, let's say, validation data? Is there some characteristics that it needs to have for quantization?
Right. Yes. So, generally speaking, the training data set and validation data set is the data set that you use to optimize your training parameters, and it has to match the statistical properties of your data, whereas your calibration needs to sort of match your numerical properties, right? And generally speaking, people treat them treat them actually in a similar manner. The point here is that your calibration data set may or may not be available to you, right? So the key is that you need to create something that your model is going to see in its lifetime. So in some sense, it's going to actually have to have the numerical properties that it's going to see it's in operation. So that's the short answer.
Got it. Thank you. There's another question that, related to something that I also wanted to ask was about removing the convolutional blocks in the MobileNet V2. Are you removing them just from the tail end inwards, or are you removing them like in any other specific manner?
A tailward, tail end.
Okay, and so a related question to that is, have you looked into other types of neural architecture search approaches instead of removing only some of the convolutional blocks?
That's a good question. I mean, the neural network architecture search, I wouldn't say I have experience with them, right? My general take away with neural network architecture search is that, it may not be sort of, specific to one implementation, but in general, it does tend to create some sort of, unstructured implementation that may not be tinyML friendly. Having said that, you can always put constraints. So I have not done enough experiment to make a comment, but on the surface, it does come out to me as being a bit not so tinyML friendly approach. But we need to kind of, study more. That's my take on it.
Right. One more question before we move on. How is the denoising implemented in the autoencoders for the KWS keyword spotting example? Was the denoising a part of the neural network, or was it a separate module like classic filtering, like median filtering? I guess denoising here is sort of intrinsic to the autoencoder functionality, right? By the encoder decoder.
Yeah. So that is actually good in the sense to understand. So let me go to that slide. So here, if you think about it, the way denoising was implemented is that we took some speech examples, added some noise, right? And that we used as X as input, and the sort of, the Y was the clean signal. So that was a very simple setup. And this is very easy to train, right? You don't need any label data set. People who have worked with KWS know that, the sort of data set labeling is pain quite a bit. Whereas here you can actually pick any data set, any noise data set, wrap it up and then you have something that you can use it later. So the setup was pretty straightforward. No special, I would say, requirement on creating how we use the data set.
Got it. And actually, just to follow up on that, compared to images where you're adding noise to the images and you're trying to reconstruct the images, right?
Right.
Here, do you add your input and outputs are the spectrogram feature maps. Do you add noise to the feature maps, or do you add noise to the audio signal directly in this case when you're simulating it?
So we add it to the time domain, because when you go into frequency domain, right, you lose some information, and it's actually a lot more. It's not always that you can recreate that in the frequency domain to the full fidelity. It's a lot easier to do it in time domain.
Okay. Yeah. Thank you. Please proceed.
Okay, so I hope, we have two more topics. So in terms of quantization, right, we have heard quite a bit. This is one of the sort of I would say, the cornerstone for tinyML, where how these quantizations are implemented so they're efficiently be deployed on an embedded end. And there are a lot of questions that you need to answer, right? Whether it's symmetric, how do you clamp it, whether you do per axis, per channel, which are the same thing, per channel versus per layer, how many bits to use, right? What optimization to use, right? How to get data statistics, and then how do you do the fine tuning, which will come in a bit, which is refers to, in some sense, quantization aware training and things like that. So there are a couple of papers I've kind of listed on the corner that has very, very good review of all these things. So
Sorry, it looks like we are having technical difficulties with the speaker again. Uh, please hold on for just a second while we reconnect him.
okay. So
Hi, Ashutosh, welcome back. Yeah.
sorry about that. Yeah, just looks like I'm assuming I was on this slide before you guys lost me.
I think your slide is not being shared right now.
Okay, all right. So let me try to do that. Share. Okay, yes. Okay. All right. So I think I was on this slide where I was kind of going through the statement that, this is a well understood problem and this works, over and over. And like I mentioned before that, the problem here is that we are actually trying to hide some of the quantization problems into the training mechanism itself, right? Where your neural network is pushing out your quantization error into null hypothesis, right, of your learning objective, right, which is sort of a problem, and I'll show a few results to highlight that. So instead, what we propose that we actually tweak the architecture a bit, and I mean it does take and that tweaking is sort of an important word here, because we don't want to reinvent the wheel here, right? I mean, this problem has been very well studied and things like that, but the fundamental issue here of trying to use the training to actually hide your quantization or numerical imperfections is not a good strategy. So generally speaking, on the left-hand side, how this quantization is done today, right, where you have some static quantization of your weights. For the activations, you look at the statistics offline with the calibration data set, and then you actually decide the scaling factors, right, which kind of gets used during the deployed, and you kind of go about it. But obviously, if your calibration statistics starts to deviate from what you are seeing in real life, it's gonna actually wreak havoc. We suggest that rather than actually doing this, we have some monitoring in the sort of real time, where you can store them in at a higher resolution, you monitor the statistics and you do the scaling, right? So this does sort of provide the protection against the things going out of distribution. And to understand this, I actually, had a quick example of where we did some post-training quantization, right, with out of distribution calibration, and this out of distribution was created by scaling, by having some sort of errors in your data and whatnot. So, and what we saw is that if you use, static quantization, right, compared to your floating point implementation, if you look at your maximum absolute error, they can actually, start to deviate very quickly, right? And they can grow a lot larger. And if a lot of, in this area, we actually pay a lot of attention to accuracy, which may mask what might be happening, behind the scene. And that is the point of this conversation here, is that your quantization, while your sort of, your learning algorithm has to understand what quantization is, you cannot be totally rely on your learning algorithms for your numerical implementation. So having a balance of both is going to actually take us to the next level, right? And I'm kind of rushing this a bit because we have still a little bit more material to cover. And so as we know, right, as engineers, nothing comes for free. So the dynamic fixed point, like we saw that it needs to actually store some extra data, and it needs to do the statistics, and it needs to figure out the scaling. So it's going to cost some extra memory and MIPS. And if you look at it, for those 4 examples, there the increase in sort of, I would say, logic is marginal, or incremental, right? It's 10 to 20%, and this is, I just used an scalar instruction set, and this can be improved if you can, optimize and whatnot. A bigger hit is actually memory, and memory is not trivial for tinyML systems, right? So we have done a bit more deep dive. So for tinyML system, where you need to create these statistics at higher bit resolutions, actually this can grow a bit, right? And for four of these tinyML examples, we can say that, it can grow as much as 60% and whatnot, which, if you see in the absolute terms, it could be, tens of kilobytes. So there is some extra penalty for having this protection, but overall, given the reliability and scalability aspect, it can bring in also the fact that it can actually solve this problem at a fundamental level. In my opinion, it's a good feature to have, right? This would help us grow beyond, what we have today. So that's the message from the quantization aspect of the tinyML. Any questions here?
So we can actually proceed. Since you said you had more slides, we can come back to questions at the end.
Okay, perfect. Thank you. So the final topic is out of distribution detection, which is sort of a topic less visited, especially in tinyML community, but must be visited, right? Because we cannot escape out of distribution, right? Things will change on the fly, right? Your sensors age, your environments changes, your operating conditions changes. There is always interferences and whatnot. As a side benefit of out of distribution network is, sort of detection, is that it can actually help design something where if you can isolate out of distribution upfront, you might be able to design systems which are more efficient, although that's not what I'm going to focus today. Today is about how to design these out of distribution systems so they are sort of efficient, and they can help us do the task we need. So in terms of out of distribution detection, I would say that something is better than nothing, right? We should not be deploying systems without OOD protection, okay? So in terms of designing this OOD protection, I mean, if you look into literature and there is a reference later, you would find basically two categories, right? Where you are doing the implicit OOD detection, where after you have trained your model, right, for your task, which could be regression or classification. Next is you actually make it a bit more robust to OOD, and that's done by schemes like temperature scaling and or calibration with your out of distribution data and things like that. The other approach, which is sort of ensemble, where you can use different models and monitor the performance over time, and or you can model your, and or you can monitor your performance of your model after it has done its job, is sort of one way of doing it. However, I mean, it's limited. The other thing is, sort of it has a lot of heuristics which doesn't scale as well. So the other one is where you explicitly use this out of distribution with some sort of deep learning method, right? And there you have two methods that are prevalent. One is sort of open world modeling. The other one is in distribution training, and we will talk a bit more about these two. So in the sort of open world, what we do is we actually create this out of distribution data and we feed it to the classifier, right? And we model this as one of the classes. This is used quite a bit. And I mean, it's a good method, it works. However, just because we need plethora of this out of distribution data, which is not always easy to get, right? It can create a bias. And it doesn't account for things, as they kind of, that may happen in the field. On the other hand, the other scheme is where you use the in-distribution data and you try to model with a separate method, and that can actually be the gateway for your final classifier, right? Obviously, this does need extra processing. It does require extra cycles. And given that it provides actually extra redundancy, this is a bit more robust solution. I mean, and the other benefit is you are able to actually use different features if you need to, right, that are more suitable for your out of distribution detection versus for your classification task. So there are pros and cons for both of them. Here is something that we have found very useful for sensor processing that we are able to reuse over and over, where we take the sensor signal and we transform it into an image signal. And we model this with a distribution method. And I think the paper that we use for actually out of dictionary detection is listed here. It's called generalized Odin. And what we will sort of show here is that in an example where we had in distribution data coming from these activities and out of distribution coming from these activities, having the baseline OOD, which is open world out of distribution versus the in distribution OOD with the pre-processing method, was able to actually get a lot better performance. And I mean, I didn't kind of go detail into these metrics because this is kind of, well understood in this community, but the idea is higher is better, right? So if you are familiar with the ROC curve, it goes something like this, and the sharper it is, the better it is, right? So you can clearly see that it's able to do a better job. So on kind of dealing with out of distribution. And finally, we kind of put all of this together. How the whole the proposal in this presentation is kind of comes together, where you take the data, you have some features, right? And then you create a classifier, you can do some transformation, send it to out of distribution. And based on this out of distribution, you can actually adapt if you need to, and then you can have a some sort of decision. So here is a simple implementation of, I shouldn't say simple implementation. Here is I would say part evaluation, right? Because there's a lot more evaluation that we need to do to be sort of, to get the complete picture. You see that having the deep methods help quite a bit, right? Even with a small data set. And this example was actually trained with a very small data set. And the quantization schemes are able to, do as well as float, right, in terms of inference. Adaptation, having the sort of dynamic adaptation, dynamic scaling actually helps with the adaptation scheme as well, right? So the takeaway from this slide is that, the whole system can be combined together in a holistic manner. And all the assets that we will develop in the process can be actually utilized just beyond what they are designed it for, right? So for example, dynamic scaling can be actually utilized in adaptation, right? So these actually do extend to other tasks, and that would help us create this architecture that can scale very well. So all in all, the tinyML techniques, right, they have matured, they have established good working development flow, right? And by tweaking these tinyML development flow, right, we can increase the chances of success. We can also unlock the next phase of success, right, for tinyML solutions. And for that matter, right, the Modos Toolbox ML, it does provide you a lot of tooling that you can help understand your solution, and you can actually, get support for dynamic fixed point if you need for your application. So that's the sort of conclusion from the talk. I hope this gives you some motivation of, where to look next for creating, the next level of refinement and improvements in tinyML systems. So I'm done. Any questions?
Thank you, Ashutosh. That was really great. Lot of great material there. We actually have a bunch of questions. Let's kind of go through them. Can you please give an example of auto distribution data? I guess in your human activity recognition slide, I think you had like some actions that are auto distribution, right?
Right. Yeah. So so out of distribution, it's everyday problem, right? One of the biggest sort of challenge that we run into is as the sensors age and or there are dropouts, right? You might have a connection. Let's say you design a platform and it's looking at some data that's coming from some sensors, and there is some glitches, right? There could be power glitches and whatnot, and it can create these data sets that you have never seen, and there is no way to actually see those. So the other aspect, which is get mingled with the machine learning aspect of this as well, and this is where I was kind of talking about the open world sort of OOD versus this in distribution, is when you're modeling, let's say a wake word detection, right, or a face detection, you are actually just modeling one class, but there is a lot of other classes that's happening. How do you handle that? So there are different aspects of it, and which one depending on which one you're trying to handle, a method can be better than the other one. Although so far in our investigation, we have found this in distribution does seem to work really well. It does need some extra implementation. So if you can afford that, it does seem to provide better performance.
Got it. And since you mentioned sensor noise, another question is, what is a good strategy to deal with sensor noise? Is it something that should be filtered out with classic filtering approaches before entering the ML part of the system, or is that something that the ML model, like a neural network model, can manage the noise all by itself?
Yes. So sensor noise, or for that matter, what we have found is that anything that's, I would say, non-impulsive should be modeled with your sort of the your model that's trying to learn the task, right? Because you do want to actually incorporate that. Whereas anything that's sort of transient and or happens, after the fact, should be handled differently. And like I said, right, you can actually have some sort of context processing, right, where you can monitor your model after things have said and done, and or you can use these these in distribution out of distribution detections. Right, which is
proceed to the next question. I mean, if there's any other details that the person is interested in, please do follow up on the forums and ask your questions there. The speaker can respond there as well. So another question is on slide 39. What is the size of the data set that you use to make those numbers? And can this also be applied to computer vision tasks?
Yes. So this was, like I said, I mean, this was actually comes out of this example where in distribution was this, the out of distribution was this. The training data set actually comes out of, believe, for these activities for, I would say, 15 minutes or so. The out of distribution was about 10 users, which are, I mean, different users in different conditions, different altitude and things like that. So.
But do you see a similar approach working for computer vision tasks as well, or is there something in progress that you'd like to talk about?
For computer vision, I mean, in principle, I would think that the similar schemes would work. The pre-processing that we have found seems to sort of, found to work. Will there be a better method? Probably, yes. But in principle, yeah, I mean, the out of distribution methods that we have talked about, they should generalize to any machine learning task.
Got it. On slide 36, what do you mean by shadow implementation?
Okay, so here, I mean, sort of in context against the explicit OOD, right, versus implicit OOD, you have one classifier that's trying to do both things, right? So now if you think about it, you are saying that, I want to model this out of distribution with a hypothesis, and my in class is another hypothesis, and I'm looking some sort of distance, right? And here you have two of these detectors, which, I mean, they're not trying to operate at the sort of the class detection, but they are trying to do some sort of in distribution modeling. So you have a shadow implementation, which is trying to do the same thing. And it sort of, starts to mimic the ensemble learning where you have more information. So you can do more with it. So that's what I meant. So in terms of out of distribution, the classifier and OOD detector can be shadow for each other. So there is some extra information that might be helpful for other tasks. So that's what I meant. I have not utilized it. It is just sort of in theory. But that was sort of an interesting observation when we were implementing this, that, for some scenarios, they are providing you similar information. And I mean, eventually that might be an interesting aspect to look into.
Got it. We have time for one more question, is asking about the microcontroller specs that you use, for example, in autoencoders and some of the other applications you talked about. Like, is it a Cortex M0, M4, M7 level of?
Right. So we use like M4 to M7, right? That is, in my mind, is a good spec for tinyML systems. I mean, it is growing and it is continuously growing. So, and that's why I didn't want to put the exact platform, because then you have a lot of dependency on the platform. And I have tried to put sort of number for a generalized architecture. But yeah, I mean, it would be, I would say, Cortex M4 to M.
Got it. Thank you. All right. Sorry, I lost your audio, I guess. Thank you for answering the questions. In the interest of time, I would recommend other people who have more questions to post them in the forums. You can reach the forums by going to tinyml.org/forums, or the specific link for this talk has been posted in the chat window by Olga. So Ashutosh, it would be really great if you could take a look at that in the next couple of days, if anybody has posted any questions there to follow up.
Okay.
All right. Thank you. Once again, thank you for the great talk. Thanks to our tinyML strategic partners, our executive strategic partners, ARM, the software and hardware foundation for tinyML, Edge Impulse enables developers to create the next generation of intelligent device solutions with embedded machine learning. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, moving artificial intelligence and machine learning from the cloud to edge devices. Our platinum strategic partners, Deep Light, using AI to make other AI faster, smaller, and more power efficient. Clickertech Global IoT Solutions. Reality AI, with pre-built AI sensing modules, plus tools to build your own. Renesas Technologies, broad and scalable edge computing portfolio. Our gold strategic partners, Maxim integrated with the new Max 78,000. The edge can hear and see like never before. Latent AI, adaptive AI for the intelligent edge. Micro.ai. NXP Semiconductors. Seed Studio, the IoT hardware enabler. SensiML, build smart IoT sensor devices from data. ST Micro, neural networks on the STM32 Cube AI, simple, fast, and optimized. SynSense, build sensing and inference hardware for ultra-low power edge devices. And our silver strategic partners, Aeon Devices, Emza Visual Sense, Greenwaves Technologies, Gravity Inc., HOTG, ImageBob, Prophecy, Kixo, Rexon, SAP, and Stream Analyze. Thank you to all our sponsors. And just a reminder, our next tinyML Talks is on Tuesday, February 1, and we also have our tinyML Trailblazer series talk tomorrow, January 19th. Please contact talks@tinyml.org if you're interested in presenting at an upcoming event. Thank you very much once again, Ashutosh, for the great talk. Let's follow up if there are any other questions on the tinyML forums.
Okay, thank you. Thank you, guys.